Okay, so we're up to the control net, which isn't dramatically different to other discussions we've had on surveying control nets, except for the height issue. So there's two options. So here we talk about a lot about total station use and other specialised equipment, but we also mention GNSS, and later on we'll mention more of it. Now, the reason we don't go overboard with GNSS is, one thing is that GNSS is a very fixed precision. Now, once you get a base station, and these days we have so many core stations floating around that, you can almost say that the precision of the GNSS is fixed. That's the upside. The downside is that you find that most GNSS systems don't work very well indoors, or in tunnels and things like that. So there are some things you probably remember in metrology, the indoor GPS, the iGPS, and there are lots of people designing systems now. I mean, there's Sydney University has a live map now, I think it's Sydney, and they've got sensors in all the, so instead of having a thing out here that you've got that says how to find your classroom, a little screen, you press the button, right? You can just do it on your phone. Or how to avoid your classroom. How to track your lecturer so that you don't see them because you haven't submitted your assignment. That's a good idea. Okay, the important thing, more important than this, than most surveys, but not all construction surveys, is you have to know where the construction is heading. Like most surveys, once you've, say, surveyed the road on a road construction project, and you've set out the culverts and maybe the bridge abutments and things like that, there's only little things to do after that. You move on, you move down the road, but your techniques don't change too much. What you did at Chainage, 1 + 500, is going to be pretty similar to what you're doing at Chainage 31 + 500. With high rise, it's different because what you do on the first floor is going to be very different to what you do on the 50th floor. So your surveying technique changes, so you've got to know where the construction's going. And of course, if you look at a high-rise site, you'll see that the construction technique changes as the height goes up as well. Okay, so you've got to be cognizant of it. Once again, very close relationship between the constructor, the civil engineer, structural engineer, and the surveyor is needed. You've got a trade-off that you should know in your head directly now. Distance is less precision, right? And that's going to be always the art for you to whether or not use GNSS as opposed to using distance and measuring equipment, right? Because GNSS, generally speaking, until you get to a big distance is not the criteria. It's accessibility to satellites, multipathing, other issues. Okay, when you start off to do the first few floors, you'll find that you can just set out 4 stations and have a little control net and it's all fine, right? As you get higher, you suddenly find that control net becomes redundant. So a little bit like your assignment where you had a very small net around the hangar, right? You've got to start looking bigger than that and go, well, that becomes redundant. So therefore, if there's any scalar issue, by means, say the control's like this, and by scale it's all out by a millimetre, it wouldn't have affected your construction dramatically. But when you've got to move to a new control, there's always the possibility of a systematic error between the old control and the new, right? So once again, knowledge is the key. If you know that's going to happen, then maybe you're setting out all the control parameters from the beginning. So there is a link between the two, you're working from whole to the part, all those sorts of general philosophies in surveying. And you can put control on nearby buildings, as long as you've got sight lines, right? And accessibility. Accessibility is one of the big issues because, you need to have the right to go into that building and do something on it, right? Oops. I'm not in slide view, sorry. Okay, so the types of control networks. This is the Al Hamra, which is a pretty large tower in Kuwait, right? This is obviously post the invasion, 94. And you can see if you look on the right-hand side here, the building shape is not easy. It certainly isn't square, right? It actually twists as it goes up. Quite an interesting shape, very pretty looking building. And if you look on the left, this is out of I think her name's same as the golfer who wrote this. It's a bit hard to see on this screen, but if you look at the green and then the centre point, they are the actual control marks around that building, the construction of that building. And the white circle is about 450 metres. So that control there, right, is actually good enough to start the building, but it's not going to be good enough to finish it. So this particular building is 400 plus metres high, which is a long way, right? So that control had to shift, but that was, I think, from memory, useful up to over 100 metres, 150 metres. And then they had to do it, use the control, but a different technique. But you put yourself in a situation, this is fairly easy because this is a remote area, right? But you go in the middle of an urban area and go, well, I'll put the building up. You put a circle 450 metres around it and you go, well, where do I put the control? The top of the Roma Street train station or something, right? Not many options. And that's why I don't outline that in the study book, but you do have access to a lot of information now. I mean, from the GIS side, you could be doing a lot of exploratory work on where you could put control just by using things like Google Earth and Q Global, or or the local council GIS, because you can see a lot of stuff in 3D. You could work out sight lines. You could even do a digital terrain model, right, to see what the sight lines would be like. So you do have the opportunity to actually look for that. And don't forget, this is money. If you have to go and set up a control point, and you think, well, the park is an ideal place. It's up high, I could put a station up there and I'm already high, right? Then you've got to deal with the council to go and put a pillar in the park or a control marker, right? So it all costs in the end. Okay, so there's the three methods, the ones you should be really used to. Intersection, right? An intersection is triangulation and trilateration. So either by angles and distances. Most cases we're talking about both, right? Intersection by total station, it's angles and distances. Resection is something that's really fell out of favour in surveying in probably the 70s, about that, until we got to the point where distance measurement became accurate and repeatable, right? So resection now is a common tool for surveyors and reasonably accurate, right? So and you'll see there are least squares. I don't know if you saw it in CompSB, but there are least squares models for resection as well as intersection. They're not very different. The difference here is vertical plumbing is the one that, as a top two, you should be aware of and be able to handle in virtually any situation. The vertical plumbing is the thing that's a little bit new, right? Because not a lot of surveyors actually do it. Not beyond the height of the instrument anyway. Okay, so intersection, then we use the same diagram here with just sample floors. In this case, we've got the 5 control points. So you would intersect points on a floor, right? Okay, to establish it. When it's lower down, you could actually use the vertical angles, the zenith distances, say height checks. But using the criticality of floor height is such that you would always be doing plumbing and measuring vertically. It's rare beyond a few floors that you would rely on a total station to give you good heighting information. Right? So in the intersection, you need lots of redundancy, right? Because we're talking about relatively high precision. We're still staying to this 2 to 5 times the amount of the tolerance. Okay. So if you've got an engineering tolerance, if it says the walls are going to be positioned in such a manner relative to perimeter columns, relative to, say, a centre column if it's there, a plinth, right? The verticality is going to be to a certain level. You can assume that any control you have, and control here is not this control. The control here is the bit you put on the floor. Because you don't set out construction work from here. You set out marks. So let's say, for example, here, these might be 2 marks that are diagonally across the floor and a set distance of, say, 2 metres in from the corner diagonals of the external part of the building. Right? And then a builder can use those to set out different things. So that's why you go the 2 to 5 times, because you have no control over what the builder does. Right? You have no control over what the engineer does. And you've got to presume their manufactured walls and things have a certain tolerance as well. So that's why the magic formula of 2 to 5 still applies. The third point, you can see as you go up, not only is the angles increasing, but you get to a point where you can't see. Here, down here, you can see a centre station. Here, you're going to get blocked by the actual building itself, right? You know, you might be able to see some corners, but unfortunately, in most building construction, you'll find the corners are where all the action is. There's not a lot of people in the middle doing stuff. They're all done on the outside. And they have all the scaffolding, right? You have crane scaffolding going up the outside. There's lots and lots of things that are going to get in your road. So as it gets higher, it gets difficult, right? You can actually do, it's quite common to, particularly with the new type targets, which are screw-in targets and things like that, to actually put targets literally screwed into concrete or screwed into formwork, right? And to measure to it. So it's possible that someone's putting formwork, say here, that you could use the control, right, and measure the formwork directly, even though you can't see past it. You know, if you do your calculations, you can measure the formwork. Now, that's another area that's not covered in this book, so we're not talking about construction, but I presume in construction surveying, you need to become adept at reading engineering drawings, you know, and understanding what they mean. It's actually very important for surveyors because often you'll be told to set something out, right? And you either they want a particular point or you choose the point. So A, you've got to be able to read the drawing to be able to calculate what point it is. And B, you've got to use the terminology that not just the engineer and not just the foreman, but the chippy or form worker, right, can actually understand. So if you write down outside of the steel, it's got to be totally unambiguous, right? It's got to be on the outside. If it's ribbed, which is not unusual for form work, right? They go, oh, you mean this or mean that? You know, it's an issue, communication between engineers and surveyors. And just remember, in an engineer's mind, surveyors are always wrong. Right? Even if they're not, they're always wrong. Okay, the last one, metrological observations. Because of the nature of these types of constructions, you've got to get used to taking good METs obs because they do affect your distance measurements in particular, right? It's a critical factor. Because you don't, when you're down here, this looks nice and simple, as though we're on grass, right? There's a million pieces of machinery there, and there's a stack up here. In the middle, there's just guys just nailing stuff, right? Drilling things with their fancy DeWalt drills or whatever, right? And you're shooting across hot ground here, machinery, all sorts of things, through pretty normal environment, onto a floor that's full of machinery and things. So knowing the measurements, it's not a matter of going, oh, you've got a thermometer, I'll measure the temperature where the instrument is. That's not going to help you when you're out here. You really have got to try to be able to estimate what the path of your observation is. Now, I keep on emphasising this in metrology and deformation because it's probably the area that surveyors least work on, and it's proven to be now, in a lot of studies, it's where we're getting a lot of error from. And part of it is because you can't see it. And when you look through that instrument and the ray of your line of sight or your laser beam is bending, right? You can't see it bending. As far as you're concerned, it's going straight. And that's one of the reasons it's difficult. You take most surveyors, I look through and say, it's very hazy today, it's jumping about 20 mil, right? They can see that. But the refraction might be 50 mil, but they can't see that. You know? And that's the danger thing, things you don't know. And good geometry right at the bottom. So you're going back once to the key points. And on the top, on the right here, this is in the Malaysian one, I think. That's a typical on the existing building. I mean, you have to dig into the ground, but you may have to get permission to actually, you'd have to grout out and drill into the concrete, right? Which means you can't touch the existing rebar and you can't expose the existing rebar to air, right? So you'd probably have to use some sort of celastic type material, right? But that's what would typically happen, is you would actually build a pillar. Not uncommon, you'll see them around. Resection, which is just the reverse of this, right? So in other words, you're looking from the floor to the marks. This is sometimes easier to do, right? Because when you're looking here at intersection, you've got to go set up on each of these. If two of them are blocked because there's someone parked there, four-wheel drive here, right? You know, you stopped for the moment. Usually you get clearer sights coming down, okay? And even though I can't sort of show it here, generally speaking, it's better for refraction as well. And remember last week when I pointed out, if the thing that's changing the height gradient of temperature is near you, your line reflects immediately and then it keeps on going that way, right? So it has a dramatic effect. When you're up here, that's why resection is sometimes the preferred method, is you don't usually have that problem for where you are. Or you have it less than you have down here, you know? So sometimes it's a preferred method, and with using things like least squares techniques, redundancy in observations, modern total stations, right? Their resection is as good as intersection, you know? Of course, the difference here is that you have to actually be up on the floor. So probably don't go into this game if you're scared of heights, right? It's probably not a good idea. That's why I'm not in it. Okay, you still need good geometry, you still need redundancy. The image on the top, which is the Burj Khalifa, right? So it's Comatech. That gives you some idea. It's not there to actually show you what, what you actually do, but it gives you some idea of actually the busyness on this is a one wing of the floor, right? So you've got a level total station, and there'll be a GNSS antennas, there's actually 4 of them, right? All on the same floor at the same time, and these guys pouring concrete and building formwork. It's chaotic, right? And one thing about construction is if somebody in construction actually accidentally bumps your instrument, right, or your antenna, right, trust me, they're not going to come and tell you, you know. In actual fact, the worst thing is they might try to put it back and go, oh, it's about there, it should be all right, you know? And then you don't know, right? That's the scary bit. Okay, vertical plumbing, which we'll concentrate on quite a bit because this is a bit different to what you're used to. So you're trying to actually carry the verticality between floors. Now we'll presume here we'll also measure upwards, right? The measuring upwards is not that complex. You can either use it with a total station, you can use a tape, right? Actually, still not unusual for surveyors to use INVAR surveyors bands because they're very thin, they're very easy to use, they're not affected by dust or refraction or anything else, right? And you can drop them through a hole in the floor, and they're very accurate, right? If you ever have to do that, just remember, I think I mentioned this last week, like inside the damn wall, look up the formula for the stress, right, or the tension of the band. When it's held vertically, it will stretch, but the corrections are usually reasonably well known. So using surveyor's band between 4 floors, for example, 4 or 5 floors, you're talking about with an INVAR band 1 or 2 millimeters. So it's pretty accurate, right? And there's no zero correction with an INVAR band. You don't have 3 parts plus million. So what we're really talking about here is verticality, right? Number one is you've got to assume that this looks easy, but once again, you're going to have a whole lot of stuff in your road, right? And oddly enough, engineers don't really like putting holes in their floors. So that's going to be worked out in advance, right? And it will be with a major project. It's when you've got like a 12-story building and you say, I didn't know you're going to put holes in the floor, you know? So if you're involved with the surveying design, the measurement model, think about these things because you don't want to get later on where you go, oh, we'll carry it upwards with some equipment down here. And they say, no, because of the integrity of the floor, right? Most buildings have holes anyway, right? So that's where looking at the design is very important, right? You'll see there's conduit holes for major equipment. There's always going to be an elevator shaft, right? Which traditionally is in the center, but it's often off-centered, right? And the elevators are usually one of the last things put in, so it is a possibility to use it. Don't use an elevator shaft if the elevator is working. If you go to a building and look at elevators, most of them stop around about 2 feet before the base, right? So unless you've got a really short tripod and you're lying down, you know, you're going to get squashed if you're in the elevator shaft. Okay, so we'll come back to verticality because it's such an important issue. You have to get used to using least squares because as soon as on one hand we're saying go for as many redundant measurements as possible, right? One of the things that, and I think I mentioned in some of the assignment answers, right, is a part of the reason you had that manual error propagation, so to speak, right, is that not everybody has least square software. Now, if your company has something like Magnet Office or Lycos, whatever it's called, their version, right, a lot of those come with least squares packages as part of it, right? But quite often they're add-ons, and if your company thinks, well, I'm not going to add on $5,000, right, or whatever it costs, then you may not have access to it. That's why we do push a bit that you understand error propagation, right? If you still take 20 measurements from different spots, you can still use manual error propagation, right? And then take the mean of what you get. And you can actually calculate the standard deviation of that mean. It will be much the same. It's that when you start getting angles, GNSS, distances, vertical distances, levels mixed together, it gets a bit difficult for you to do in the spreadsheet. Okay. So it is always going to be a two-stage process because you don't go straight from control to construction, generally speaking. And the main reason is because you try to put your control in situations or positions where it's least likely to be damaged, which means that it's going to be away from the site a bit. So you tend to go from control to localized control. On high rise, we would tend to go from control to what you would call virtually temporary control, because most things get destroyed very quickly. So you go to control to something you can use for the next week or whatever, right, on that floor. But once it's gone, it's difficult. Okay, stability. In our case, we've discussed stability in ground and in other areas. Here, vibration is an issue, right? So you might think that it shouldn't be an issue, but I shall come back to total stations later, right? You'll see it's a major issue. But things like levels, what you consider this the standard automatic level, digital or automatic, manual, analog, doesn't make any difference. Anything that requires a damping compensator effect, right? Because you don't know what those vibrations are, you don't know the frequency of them, anything else, they can get hung up, right? So more importantly, when we talk about vertical plummets, it's exactly the same. A vertical plummet operates on the same principle, right? That you must ensure that the compensator is freely swinging. So if you're not used to doing that with your normal leveling, make sure you do it always on construction. So if it's got a button, press it, right? But if it keeps on swinging and staying in one position, and you swing it around, it doesn't move, right? Then you've got a problem. Actually, if you look at old surveying text, you'll see everything on high rises was use a spirit level, which you physically level yourself, right? Because there was a problem. That was a lot because there were steel floors, right? Steel floors had more vibration in them during construction, but we still get significant vibration in high-rise construction. And it can affect, it doesn't just affect the instrument, it also affects, you set things up on a tripod, right? And you might think that's stable. When the thing starts vibrating, legs creep, you know what I mean? So there is some ways around that. I didn't do much of this work in Australia, but in other places we used to use plaster of Paris or something similar, right? I'm sure you can get some goo that you can spray on or whatever, and we'd actually plaster the legs in. It's not going to last forever, but it's enough usually for that period of time to keep us stable. Atmospheric conditions, like I said before, best way is to measure them, because if you come back later on and you've got areas that you don't know about, you could then look at the atmosphere at your measurements and go, did that impact on it, right? But a lot of the random sources are really difficult to evaluate. You might know they exist, but you mightn't be able to evaluate them, right? So a good starting point is know they exist. Now, after this course, you should be more and more aware of the existence of certain types of errors, even if you don't know exactly how to get rid of them, right? Knowing about it's a good start. Okay, now you should have had enough pre-analysis by now to last your lifetime. After the last assignment, right? Actually, someone actually made a comment about this assignment that we should have put a dash in pre-analysis, because I always write it as one word. It saves one keystroke, you know. But with building, this is a simplistic one. Obviously, that complex building like the Burj Khalifa, pre-analysis will be important because you've got the three wings, right? And very big changes in the floors, you know, and the way their shape is. But generally speaking, you're going to start from something outside and there's a target, right? So if we've got the simple case here, which is in the study book of a building floor of 40 metres by 40 metres, so like, I don't know, 3 times the size of this lab, right? Then you can actually work out and go, what are the total station specifications, right? Which you should be fully aware of. You've done enough of this now, okay? And for those few people who actually put down, I'll improve it by putting the input as 95% confidence level, don't do that. Just try to, it's easy, just try to remember when you go to 95%, do it at the end. You make less errors then, right? So operate on everything on a standard deviation and then change it at the end when you want to evaluate it. So this is actually, I mean, this is pretty good, but it's what current total stations claim, right? Okay, now if you go to a used car salesman, you buy a car and he says, this is a 1500cc, right? You'll probably find it's 1430, ramped it up, right? It's in beautiful condition, driven by a little old lady, right? I mean, you're not going to believe it. Surveying manufacturers have slightly higher ethics. But what's in their manual is what they would like it to be. Okay? Now, I emphasise this point because we're talking about precision surveying. It's something we didn't mention in the assignment because we didn't want to confuse that question one any more than it was. But you can't keep on going, I'll take 100 readings. You remember last week I pointed out to you that whilst you can't work it out, a lot of that, this 0.8 of a mil, right, is actually in manufacture, right, or electronic noise. But a lot of it will tend to be a systematic error. In other words, we can't tell any better than, say, 1 millimetre, right? And then a lot of this parts per million is the variance that exists in the frequency counter, or the frequency generator. But that can also be systematic, right? So you can't keep on going down and taking this instrument and saying, I'll do it 20 times, and we'll end up with 0.1 of a millimetre and, 0.01 parts per million, because that would be unrealistic. Because there is a systematic error in there that you can't get rid of. So take that as it is, but presume that's as good as you're going to get, right? Actually, you'll always see there's a little footnote saying, under ideal conditions, on a nice sunny day when you're really wide awake and there's 27 surveyors doing the same instrument. So if you take this simple case here, right, we've got to sort of say then the pillar control to end up with what the tolerance is in the middle, it's got to be 0.25 of a millimetre, right? To end up with targets on the floor of 0.5 of a millimetre. You guys aren't used to actually dealing at 0.25 of a millimetre. I've seen you with total stations. Most of you look through and you look at the thing on the ground, you say, oh, it's on the top of the nail. That's good enough. Well, that's about 5 millimetres. So it gets very difficult, right? The only way you can get this stuff is through redundancy. You're not going to measure once and say, yeah, I got it. Perfect. It's going to be taking a number of measurements such that you actually are getting it close to it, right? And if you can't get that, then you immediately got to say to people, okay, the 0.5 of a millimetre on the floor, which then equates to maybe 2 millimetres for the constructor, right? If the constructor says, oh, I've got to do it to a millimetre, you've got to start saying it can't be done. There's nothing wrong with you actually having an input because you happen to do SVY 3400 and you know all this stuff, but you can't go back and say, I've calculated it, and if you want to impress an engineer, do like you did in the assignment, write all those pages, put a whole bunch of tables. You got it straight away, right? Because they're not good with numbers, so, you know what I mean? They're good with concrete and things like that, but not with numbers. So this is, if it's unrealistic, be practical about it and admit it, right? Atmospheric effects, you can see this, 10 degrees Celsius. Now, you would notice it here. If it's suddenly 10 degrees hotter, right? We won't notice it in the lab, but we would notice it outside. You'd feel it, right? But you go on any construction site at 7:30 in the morning or 6 o'clock in the morning, right? A 10-degree leap between when the machinery starts up and you get on a floor or you go underground or you come above ground or you're up 5 floors, it's nothing, right? So 10 degrees is about 1.5 parts per million. Now, you've just bought this, 85,000, actually, that level's probably $120,000 worth of total station these days, right? Because it goes to 1 part per million. You don't measure the temperature and you're already out more than the spec. It's a package. It's the error budget, right? And no error estimate for the vertical horizontal refraction because you don't know what the estimate is. Totally unknown. When you don't know something, everything else has got to be better, just in case. Right? The trig heighting component, if we're measuring heights, right? It's not perfect, but that's a rough idea, right? 2 parts per million and plus or minus a millimetre on the target. And I think that's optimistic. You think about most of the prisms you use, and the ability of ATR, right, to actually get down to that level. Once you get below a millimetre or 2 millimetres, you're really talking about, you've got a bit of luck on your side. So it's difficult. If you're working on sites like this, you're doing control, there's 2 things you don't be cheap on. Don't be cheap on targets, right? Don't buy the ones out of Shandong province, right, because they're... the eBay special ones, because whilst they will give you a distance, you can probably guarantee their quality of manufacture will probably be less, right? On the other side, Leica's for $450 targets, you know, they would be there, you know. There is probably the quality control that you would expect out of Leica or Topcon or Socair or Trimble, you know, and that's part of their marketing is to have that. So, and single set observations. This wasn't explained very well in your last assignment because we just want you to learn about what you're doing. A single set of observations is basically a face left, face right, and a distance, right? Total station, normally face left distance, face right distance. So you've already got two distances, okay? But you've got to assume to yourself, because it's been done immediately at that time, that they are what we would call correlated. You know, so just saying, oh, I've done two distances divided by √2 and I've got improving the precision, right, is sort of valid on paper, because of the correlation, you would be better off taking one distance then and one distance 10 minutes later. You know, the difference in time means that because you don't know about refraction effects, change in meteorology, then it's more likely to be a better estimate of the mean than those two very quick ones, right? Doesn't mean you don't take them, it's just that you don't just do that and go, oh, we won't do any more sets. You have a big advantage now is that years ago, this actual element, a lot of work was on precision pointing and things like that, because to take another round of angles with a theodolite took a lot of time, right? You know, it's tiring, it's slow, you know, and to take more distances, I mean, now you actually have to move your hand all the way from like the telescope, or sometimes you don't because you can just voice over, touch the button to press the distance. That's a little bit faster than actually taking the theodolite off, unpacking the EDM, putting it on the tribrac, remeasuring the height, kicking up the car battery that you've taken out of the car, right? And hopefully it's going to keep going when you get back in the car, and just to take an extra distance. So in previous generations, you would have actually avoided multiple observations. It's one of those things now that, you know, you take. But you always think, have that in your mind, if you're trying to get rid of systematic errors, don't do a multiple observation unless you recheck that you're over the mark. Like if I was doing precision work in something like this, you know, setting out control, not only would you do sets of observations, but I think you are also better off just leveling the instrument, resetting it over, if you're particularly over a ground mark, right? Resetting it over the mark, then taking another set of observations. Because then you've truly got two independent observations. There's no use saying you're down to 1 part per million, right, if you've drifted off the mark by 3 millimeters. You know, there's no gain. Okay, so that's what it sort of looks like if you look at it in tabular form, which you should be very used to now. So we're going on a floor basis, right? And you can see that actually in this case, if you look at this intersection and resection, we've actually got the control points, right? The floor level, and this is up to 50, right? And sigma x, sigma y, and sigma z is interpreted at the moment, right? For measurement. You start to see that you're losing sigma z, you know, a lot quicker than you're losing here. And you see here the resection method, when you start losing here, like I was saying before, as you get up on the floors, the resection method starts to be better, right? You know, it's just nature of being able to have better sites. That's a purely mathematical formula, as opposed to the practicality of a site, where you would favour the resection method because of the practicality. Okay, the engineers will tell you this, the setting out of the raft and the first floor, you know, if you don't get that right, the rest of them start to fall down, right? But in reality is that you've got a plan to set out to be the same for every floor, you know? You just make sure you don't make a blunder on the first floor, because if you make a blunder on the second floor and the guy's putting the column in, he thinks, that's strange, I would have thought that column should have gone straight over the top of the other one, right? You know, it probably will show up, but if you make a blunder on the first floor, it may not show up. Oops. Okay. The base of the high-rise structure is one of the key monitoring points for static changes. So the settlement, right, or twist of the raft, the foundation, they will have a lot of monitoring in it. And you'll see, actually, you're talking about, I think the Burj Khalifa has something like 180 different monitoring points, right? It's quite large. Your height datum's got to be critical on the first floor, because you measure a lot from that point up, right? So your control has to be good. And it's not unusual to put a lot more extra height stations around because you can level reasonably easily between stations, setting up benchmarks, right? And you're not too worried about the XY movement. You're not too worried about the vibration with them, right? If you're doing that, if you have access to it, use a precise level. Even if it's only over short distances, you know, it's no use using a normal level, say I'm getting one, you know, I've got third order leveling, you know, it's 12 millimeters square root K, and that's great. It's not good enough for construction, right? It has to be better. If you don't have a precise level, do a number of level runs. It'll improve it, right? Not 100. Stacks of redundancy in the datum, right? We haven't covered a lot of it, but you'll see in least squares, if you read a bit further with it, that blunder detection is one of the biggest things, right? Standard has it in it, most of them have it. But blunder detection relies on you having a knowledge of the geometry, usually better approximation of coordinates, you know. So often you don't do blunder detection until you've actually started to set out, right? Now, one of the things we've been talking about in least squares is that we sort of do this pre-analysis with approximate coordinates, and then you do the survey later on. Generally speaking, there's a second pre-analysis, right? If you can do some of the measurements and get more real coordinates, you know, or closer to it, right? Often people will do a first pass adjustment. That's a blunder detection, right? But once you do any survey after that, any complex control survey should do a blunder detection at any time, right? They're not totally reliable. I mean, there's lots of ways of doing it, but it's better than nothing. Okay, precise leveling, particularly in the control net, is critical, right? You know, there is no substitute for that. In actual fact, a total station over clear ground with not refraction problems is usually better than a third order level these days. You know, if you're 150 metres away or something like that, it's pretty good, right? Particularly if you've got redundant observations. You know, measuring the height of the target is critical, right? And that's why people tend to go for maybe not necessarily pillars, but fixed total stations. And when they do the work, they actually use force centering. Everyone understands force centering, yeah? So, you know, you've got to eliminate those errors out of your equation. When it says far enough away to not be influenced by ground movement, that's a judgment call. You can ask the engineers, right? But quite often they won't know. In a city block, you can presume they will have done work on it because they don't want the building next door shaking, because people get upset and they sue you, right? So there will be, a geotechnical engineer could probably give you an indication of that. But presume that ground movement will change as the building changes. You make that assumption. The first stage is the heights are then carried up or down. Don't forget, in most of these buildings we're talking about, there's 1, 2, 3 or 4 basements, right? So you're not just going up, you're also going down, right? Which is sometimes more difficult. It's sometimes more difficult. You have no external sight lines. You actually have to go down by plumbing. There's no other way of doing it, right? You can't use GPS, right? You could use a gyrotheodolite. There's some new gyrotheodolites that are quite good, but I can't see any surveying firms buying a $40,000 gyrotheodolite just to use for basement on one building. Okay, this just gives you some idea. This is the Al Mara Tower in Kuwait, and this is their monitoring schedule, right? Now, the surveyor is involved in this because even though you might not be the one who puts in the tilt meter or the extensometer, right? You're the one's going to say where it's going to go, because the design and the structural engineer will go, if we put it there, that'll measure a certain thing. But there, that's where the surveyor comes in, right? You've got to locate it. And you might be involved heavily with the monitoring. It's a field that surveyors, I think, should get more involved in because they have the skills for it, particularly to interpret the data, right? So there's 14 monitoring points here. Beginning of the project, we're talking about static movement, particularly, right? So weekly base monitoring was more to go, did we do something wrong, you know? I mean, if the foundation's moving on a weekly basis, I think you'd be getting a bit worried, right? You know, someone forgot to pour some concrete somewhere. It gets less later on, in case there is no problems. Then the maximum settlement is, and this building is here, right? And the minimum settle is the green circle, which you can hardly see on that, just at the top. So we're obviously talking about a line here. That would represent a tilt of some sort, right? Okay. So you can see the settlement, like the ground floor to the top level, I think this was, did I say 80 floors before? Was 85 millimetres, right? So it wasn't in one spot, 64 millimetres minimum, right? That's a fair bit. Significant enough, right? Obviously it's over a fair distance, but you can see that it's significant. Okay, the other reason for monitoring is, as I mentioned before, concrete shrinkage. If you're working on a site like that, you should be able to get from the geotech guys, right, the structural engineer, the predicted settlement. Now, if they say to you, just give us the data, we'll work it out, you know, because they're treating you like a dump surveyor, right? You know what I mean? Don't accept that. Because of the difficulty of working on these sites, if you take a measurement, it's good for you to be able to go, oh, that's sort of within what we expect, right? And if it's not within what you expect, what a good surveyor will do is go out and redo it. I'm going to make sure I'm not wrong, right? You know, so if an engineer says, oh, you just give us the data, you know, just remember that we know mentally you're superior to the engineer, right? Maybe not physically, because there's big engineers around these days, right? But you should always insist on being treated with the same level of technical capacity as they supposed to have, right? And so, or purport to have. But that is one of the issues, is always give yourself a bit of an edge. You're the one measuring so many things that it's very easy to make an error, right? So give yourself another chance to pick it up before someone else does. The other thing with settlement is to always remember that if someone says we're looking at the settlement of the concrete, it very rarely is even, right? So if you are looking at settlement, particularly on the base floors, try to get a number of points, key points around the floors, right? If there are pillars, deep-driven pillars underneath the raft, right? Try to get measurements of the settlement at those points and then between them, because the settlement might be dipping between the two, or the points might be sinking and then it would be bulging in the middle, right? So it's fairly easy to think about. If you ask an engineer, just ask them where the bending moments are likely to be. You know, that's the sort of terminology they would use. Okay, so you could get the floor height, you could measure it directly, right? As I say, they're less commonly now. Total station in a vertical mode. I know you probably haven't done this, but if you just turn the telescope up, it still measures. I mean, the laser beam isn't real heavy. It's like it goes up and crashes down, right? So you still measure in that mode. It's not an issue, not to. And there's probably less errors in that mode because in most situations you're going through what I would call clean air. You don't have as many refraction or changes in the path of the ray. Or by GNSS, which you know when we're talking about heights, doesn't matter how many core stations have floating around, it's always got a problem, right? And more recently, of course, there's the electronic noise for heights in what they call the electronic center. You've done this in GDB. Electronic center in GNS antennas is pretty poorly defined. So it's a systematic error, right? And it's a difficult one, apparently, too. It's not my area, but it's a difficult one to work. Flatness, we discussed this in metrology, right? It's not going to be the level we're talking about there, but floor flatness is not whether it's tilted, right? That's a different thing. Floor flatness is whatever the plane it's in, is the deviation from that and the plane itself, right? So the reason for floor flatness might be installation of equipment. It could be that if they're using a core and wall technique, right, that the walls are prefabricated, so there'll be a tolerance on the walls themselves, right? Usually fairly generous. I mean, it's not, you'd have to make a blunder to get that totally wrong, right? But generally speaking, you may be called upon to do floor flatness. Now, you can't measure floor flatness from down here up there, right? You have to be on the floor. That's when the vibrations, sway, and things come into account, right? So always remember, I mean, it sounds silly, but if it's vibrating that much, go onto eBay or find some old retired surveyor who's probably got equipment sitting under the back shed, right? And give him $20 for an old spirit level. They're just as accurate as an automatic level. They're just slower, but they won't vibrate. So there are some advantages of having old-fashioned equipment, right? If you've got a really old one, you just buy it and resell it because they're worth a lot of money these days. Now, also, this is something that I call it as-built, but I think compliance surveys would be a common term now, right? You still have to do it for buildings. You have to do it for anything that's got a contract. And it's a lucrative part of surveying. Don't actually let some contractor say to you, oh, and of course you'll do the compliance survey, right? Because to do a compliance survey properly is a fair bit of work, right? And it's a little bit like we talked about the gap between tolerance and control. There's not much you doing a compliance survey that's less precise than the original. You're not checking anything. So you do a compliance survey, it should be more precise than the original. If you do have to do compliance or as-built surveys, right? Even though these days you might well do it with a laser scanner for a lot of it, right? For the as-built. Think about your control right from the beginning. You go, would this control be suitable for compliance or as-built as well? The answer might be yes. But it might be that if I put an extra point back here, that would be good for scanning, right? Or whatever. And in high-rise, of course, as you probably know from your extensive studies in laser scanning, it works great when you're in this room and you scan the walls and make a 3D thing and you put in, people, or not people, what do you call them, MEMS or something floating in front of the computer, right? Then it looks great. But when the thing you want to scan is, 200 metres above you, it not only quickly can't you see it, but quickly loses its accuracy. Most scanners have a very strong limit on what they can do, right? But there are some new techniques, even from your close-range photogrammetry, UAV imagery on the sides of buildings, where there is control. In other words, you put a target mark on the side of a building and you fly it, right? There's no reason for you not to think of that as just the same as vertical photography in a horizontal mode, right? If the surveyor's got targets there, you can resolve that quite easily. About going back to that, the other thing I mentioned there was that with most high-rise, compliance or as-built is not necessarily done at the end, right? The engineers will want to know, I think mostly a 2 to 3 floor basis, because you tend to be doing work on this floor. There's a crane on 2 floors above you on scaffolding, right? Or crane base, right? And there'll be a floor being finished in the middle and a floor actually being poured, while the formwork being done on top. So 3 floors is probably a reasonable estimate, It can change. But they'll want to know underneath there what the as-built is, right? A, it's monitoring, and then B, is there a problem? They don't really want to get to the 10 floors up and go, oh, by the way, we sort of made a mistake down there. It's a bit late to correct it. Okay, so the theory here, and this is now getting the more complex bit,